In this video, we're going to be looking at topic 3B, rates of reaction, in the IGCSE chemistry course from Edexcel, and we're going to be focusing on the double outcomes. If you're a single or a triple student, you can check out those videos on the YouTube channel. So we're going to be looking at experiments that we use to describe the effects of changes in surface area, concentration, temperature, and using a catalyst. We're going to be able to both describe the experiments, the effects that they have, and we're also going to be able to explain the effects using collision theory. We're going to be looking at what a catalyst is and how a catalyst actually works. So let's start off by looking at how we actually measure a rate of reaction. So a rate of reaction is all to do with speed, and it is the speed at which a reactant either decreases or a product increases. So we define it as the change in concentration of reactants or products per unit time. Now that's very important that we always relate the change to time, and we can calculate it using this equation here. So we've got our change in our concentration, our volume, or our mass divided by the time in which this change happens. So if we start off by looking at an experiment, and this is one that comes up in exam questions quite a lot. So we've got marble chips reacting with hydrochloric acid. Now the marble chips are made of calcium carbonate, or CaCO3. And when they react with hydrochloric acid, you should know from the acids and bases topic that they are going to release carbon dioxide gas, because this is a metal carbonate and an acid. So we have this reaction happening here. Now in this particular experiment, we don't really care about the salt and the water. What we care about is the carbon dioxide. As the carbon dioxide is released, what happens is mass is lost, because that gas is being released from the conical flask. So you will see that you may start at a specific mass and you will finish at a lower mass. Now that mass that is being lost tells us how much carbon dioxide is being given off. So we can then plot that volume of carbon dioxide released, and we can plot it against time. So this is your volume of carbon dioxide released, and we plot that against time, and what happens is we get this nice curve happening here until it levels off, and when it levels off, that means the reaction has stopped. Now we're not particularly interested in the actual part where it is leveled off, because the reaction doesn't happen. We are interested in this section here, and we look at the slope of the line. So when we're looking at a graph for a rate of reaction, we are looking to see, is the slope steep or is it not steep? And the steeper the slope, the faster the reaction, because that means that the change in concentration or mass is happening faster when we have a steep slope. So if the change is happening faster, then your rate is higher, or the reaction is happening quicker. Now what we can do for any part of the graph is we can calculate the average rate, and that is looking at any time interval. So if we wanted to look at the rate of reaction in the first minute, we would go to the graph and we would look at, in 1 minute, how much gas has been given off, and we could calculate that we give off 0.47 grams of gas every minute. So my rate in the first minute is 0.47 grams per minute. If I look at the second minute, I look at how much is released between 1 minute and 2. So this amount here, that's my change in mass. And in this case, it works out to be 0.2. So my rate in the second minute is 0.2 grams per minute. You can see that as the reaction proceeds, or as the reaction continues, the rate gets lower. The reaction is always faster at the start. And we could average over the first 2 minutes as well if we wanted to look at that particular rate. So the rate of any chemical reaction will be the fastest at the start. So your graph is steep when it is fast. As the reactants start to use up, your rate is going to slow down, so your graph becomes less steep, it starts to level off, and eventually the reaction will stop when all the reactants, or one of the reactants, has been completely used up. And when that happens, the graph becomes level. So we can use our experiment graph in order to tell us a lot about the rate of reaction. Now, when we're talking about rate of reaction, we need to understand how the reaction actually happens. And in order to do this, we need to discuss collision theory. If something is colliding with something, that is another word for hitting. Now, in order for the particles to react, they have to collide or hit into each other. And a chemical reaction can only happen if the reacting particles collide with enough energy or speed. And we give this amount of energy that is required a specific name. Now, this energy is trying to overcome the forces of the attraction between the atoms and the molecules to start breaking the bonds. So if we've got, let's say, oxygen wanting to react with carbon, we are going to need to break this oxygen bond in order for the reaction to happen, and we need to have a certain amount of energy to do that. And this minimum energy is called the activation energy. And this is the minimum energy required for any reaction to happen. Now, every reaction will have its own individual activation energy. Do not worry, you are never going to be asked to calculate it. You just simply have to know the definition of activation energy so that it is the minimum amount of energy required for the reaction to happen. If we have a collision happening with an energy greater or equal than the activation energy, then we call these successful collisions. So that means that in this first one here, molecule A and molecule B are hitting each other with enough energy that is higher than the activation energy for them to react. And then we make our compound products. Whereas in the bottom picture, you can see that A and B are hitting each other, but they do not have enough energy. So the energy that they are colliding with is less than the activation energy. So this is an unsuccessful collision. And you can see that A and B just bounce off of each other. When we are discussing rates of reaction, we are always wanting to look at successful collisions, and it is very important that we are using the terms frequency of successful collisions, because we want, in order to increase our rate of reaction, we want these successful collisions to happen more often. So we'll look at an answer in a past paper question towards the end of this video that will show you the key terms that you have to be using each time. So let's look at the number of factors that can affect the speed or the rate of a chemical reaction. And there are 4 that we have to know. There's particle size, concentration, temperature, and catalyst. Now, sometimes in concentration, they will also mention pressure when they're talking specifically about a gas, but they have the same information. And you have to be able to not only describe the effect, so the rate increases or decreases, you have to be able to explain it. But they're actually much more simple than you think. So let's start off with particle size. When we have any solid, our chemical reactions can only take place at the surface. So if you have a block like this, right, my chemical reactions can happen at the surface here, but all this part in the center remains unreacted. So the smaller we make a solid, the larger our surface area is going to be. So we are increasing the surface that the reaction can take place at by making the particle size smaller. So in order to speed up a reaction, we need to increase the number of collisions, and it is the number of successful collisions in a specific time frame. So the more collisions that happen, the more products are being produced. So what does this actually look like? Well, if we take a solid and we put it into a powder, you can see in the diagrams that we're getting this increase in surface area. So if we have one big lump, all of this part in the center here is not going to be able to react. Whereas if we change it into smaller pieces, the parts that can react, we make much smaller. You can see there is very little that will actually not react here. So this allows for more frequent, successful collisions. And when we have more frequent successful collisions, we get a faster rate of reaction. If we think about concentration, a reaction speed can be altered by increasing the concentration of a solution or the pressure of a gas. And what happens here when we increase the concentration, we are increasing the number of particles in a specific volume. So we go from having maybe 3 particles to having many particles. And the more particles that we put into this volume, the more likely they are going to come into contact with each other. Therefore, the more likely they are to collide. So you can see that we see this diagram here. In this low concentration, we get 1 successful collision, and the higher concentration, we get 4. So increasing the concentration means we have a greater number of successful collisions, therefore giving us a faster rate of reaction. Again, we can look at the temperature as another factor, and when we increase the temperature, all of our reactant particles are going to have more energy. So this means that more particles are going to collide with each other, so they're going to collide more often and with more energy. Just imagine if you took a room full of people and you asked them to walk around a room. The chances are they're not going to hit into each other. But if you ask the same room of people to run around the room, they are more likely to hit each other. It's exactly the same with our particles. The faster they move, the more successful collisions, therefore a faster reaction. And pressure is very much the same as concentration. We are increasing the number of gas particles into a specific volume. Therefore, they're closer together and they can collide more frequently. So increasing the pressure, be aware, will only affect gases. Any particles in a solid or a liquid are already too close together, so pressure would have no effect on the rate of a reaction if it was a solid or a liquid. This will only work for gases. So we go from having our particles in this large volume into a much smaller volume, so you're going to get more frequent successful collisions. Now, the last way that we can speed up a rate of reaction is using a catalyst. So you've learned back in Key Stage 3 this definition of a catalyst. So a catalyst is a substance which speeds up a chemical reaction but is not used up in the reaction. Okay, and this, because they're not consumed, we only use very small amounts of the catalysts, and we can do that to process lots and lots of particles, and different reactions are going to need different catalysts. For example, the Haber process to make ammonia uses an iron catalyst, whereas the contact process, which makes sulfuric acid, uses a vanadium catalyst. Now, you're not expected to know these are just some examples for you just to show that different reactions need different catalysts. Now, living things also make use of biological catalysts, and we call these enzymes. And these are proteins that allow reactions to take place faster at lower temperatures. Because remember, our body temperature is roughly 37 degrees Celsius, and most of the reactions in our body wouldn't take place quick enough at this particular temperature. So we use enzymes in order to allow this reaction to happen because the enzyme acts as a catalyst. You'll learn more about that in biology. Other examples of catalysts are manganese oxide and lead oxide, which we use to catalyze the decomposition of hydrogen peroxide. Now, when we're discussing catalysts and we're saying that they're a substance that speeds up a chemical reaction without being used, that's a key stage 3 definition. In order to make it a key stage 4 definition, we want to link it to our activation energy. Remember, our activation energy was the energy required for the reaction to happen. So what a catalyst does is it provides an alternative route for the reaction that has a lower activation energy. Now, we cannot say that a catalyst lowers the activation energy. Okay, we have to use this here, saying it provides an alternative route. If the activation energy is lower, then more collisions are likely to be successful. And the reaction is going to happen faster because more particles have an energy that is greater than or equal to the activation energy. Okay, so what we've done is we've not changed the energy of the particles, but what we've done is we've made the energy lower to make it easier for the reactants to react with each other. So they can hit each other and react much more easily because the minimum energy needed for the reaction to happen has been reduced. So if I have no catalyst, I might need 50 kilojoules of energy. If I have a catalyst, I may only need 20 kilojoules of energy in order for the reaction to happen. So we are reducing the activation energy by giving it an alternative route for the reaction to happen. So let's have a look at a past paper question for this. So a student uses this particular apparatus to study the rate of reaction between marble chips and dilute hydrochloric acid. And she uses the method where she puts a conical flask on the balance, adds 15 grams of large marble chips, 25 centimeters cubed of acid, records the mass, and then starts a timer, and then records the mass every 30 seconds until the reaction ends. So we want to explain what happens to the mass of the flask and the contents during the reaction. So if we go back and we have a look at the equation, this is the one that we mentioned at the start of the video, we are going to be giving off carbon dioxide gas. So our mass will decrease. And the reason that the mass will decrease is because CO2 gas escapes from the flask. So all of our CO2 gas is going to be released from the flask or leave the flask or escape from the flask, so our mass is going to decrease. For part 2, we want to say why the reaction ends even though some of the marble chips remain in the flask. So again, let's go back to our reaction here. So we've got hydrochloric acid and our marble chips. So if we have some marble chips left over, it means that there must be nothing else for it to react with because my reaction has stopped. So that is because all the hydrochloric acid has been used up. Or the hydrochloric acid has reacted, there's not enough acid to react with the marble chips, something to imply that there is no more hydrochloric acid left. And how would the student know when the reaction has ended? Well, it will be when the mass of the flask stops decreasing, because we will not have any more carbon dioxide gas being given off. So that's going to then stop the mass from decreasing. Eventually, the mass will just stay the same. The student then plots her results on a grid, and we're then looking at what time the rate of reaction is the greatest. Okay, so we want to be looking at the steepness of the curve. So at 1 minute, 1 minute is going to be here. At 4 minutes, 6 minutes, and 8 minutes. And you can see very clearly at 1 minute, this has got the steepest curve. So our reaction will be happening the fastest at the beginning, at 1 minute. And we know that in two ways. One, the curve is the steepest, and two, it is the beginning of the reaction, and that is always when the reaction happens fastest. So the student repeats the experiment with the same volume and concentration of acid, very important, but with 15 grams of smaller marble chips. On the grid, sketch the curve that we would expect. So before, we had large marble chips. Now, we have smaller marble chips. So we have decreased the particle size. By decreasing the particle size, we are increasing the surface area. Therefore, we are increasing the rate. So this reaction is going to happen faster than the one that is on the graph already. So our curve is going to be steeper. But notice, if we go back, we used 15 grams of large marble chips, and we are using 15 grams here. That tells us that the mass that is being lost has to stay the same. I've not changed how much marble chips is reacting, I'm just changing how fast they are reacting. So my curve should start at 0, and it should be steeper than the one that is there, but it will level off at the same point, because I must be making the same amount of carbon dioxide, I'm just making it faster. And then for part C, explain how decreasing the concentration of the hydrochloric acid affects the rate of reaction. Refer to particle collision theory in your answer. Now, when you're answering one of these questions, they will almost always be a 3-marker. And you should follow a very specific way of answering these. So you should explain or describe what the effect of decreasing the concentration is. Well, decreasing the concentration is going to lower the rate of reaction. Okay, so my reaction rate is going to be slower. Why is the reaction rate slower? Well, if I decrease the concentration, I have fewer reactant or acid particles in a specific volume. That is me describing what decreasing the concentration actually looks like. I am decreasing the amount of particles I have in my specific volume. Why does that cause a lower rate of reaction? Because I have fewer successful collisions per second. I must always link it to time. Another way that I could phrase this, however, is I could say I have less frequent successful collisions. When you are answering a rate of reaction question, you should always use this phrase somewhere in your answer. You always want to be discussing less frequent successful collisions. So it's about linking how many successful collisions you have and linking it to a time. That is how you answer a particle theory question, and they will almost always be 3 marks. So you say what happens to the actual rate, you explain the effect, and then that either increases the frequency of successful collisions or it decreases the frequency of successful collisions, and that is your 3rd mark. You can have a look at the mark schemes for these questions that we've just went through, so you can see that, again, focusing on the frequent successful collisions. That's everything for 3B rates of reactions for double. If you have any questions, please feel free to leave a comment below, and hopefully we'll see you back on